Hi everyone, I'm Yugo Nagata. In this session, I would like to talk about my proposal to implement the feature for updating materialized view automatically and incrementally. First, let me introduce myself. I'm Yugo Nagata, software engineer at SRA OSS Inc. Japan. I'm in charge of research and development on PostgreSQL, and now I'm working on incremental view maintenance. That's today's topic. This is the outline of this talk. First, I'll introduce incremental view maintenance, IVM. Shortly, this is a way to refresh materialized view rapidly. Next, I'll explain our implementation of IVM, its outline and details about how it works. Then I'll show some behavior example, including performance evaluation. Finally, I'll summarize this talk. First, view is a virtual relation defined by a view definition query. The query is executed when the view is referred to by a select statement. On the other hand, materialized view is a view whose results are stored in database, so it enables quick response for client. This is useful for data warehouse for analyzing large data. However, materialized view needs to be maintained after a base table is modified to keep consistency between views and its base tables. Refreshing materialized view is one way to maintain the view. In the current PostgreSQL, the refresh materialized view command. When this command is issued, the view's contents is recomputed from scratch, so it takes a long time. By using concurrently option, a refresh materialized view is performed with a weaker lock, but it still needs recomputing. Incremental view maintenance, called IVM, is another technique to maintain the materialized view. It computes and applies only the incremental changes to the materialized views, so it is effective if small fraction of the view is updated. This figure represents IBM informally. When we have a base table D and view definition query Q, we can get the contents of a materialized view V. When a base table is updated, we can get changes on tables and updated base table. And this updated base table and view definition query, we can get updated materialized view. This green line is recomputing. That is what refresh command is doing. On the other hand, if you can get changes on view from changes on table, we can compute updated materialized view contents by applying these changes to all the view contents. This red line is incremental view maintenance, IVM. IVM is not supported in the current PostgreSQL, so we developed it and the patch is proposed to developers mailing list. The subject is implementing incremental view maintenance. Using this feature, materials view can be updated automatically and incrementally when its base tables are updated. So you can get the latest state of the view just after table changes, even in the transaction. Of course, you don't need to write trigger functions by yourself. As a view definition query, we are supporting selection, projection, and join, including self-join and outer join. And we support distinct clause and views with tuple duplicates. Now we are supporting some aggregates with or without group by clause, count sum average min max. And in addition, we are supporting exist clause, simple subquerying from, and simple CTEs. So how effective our IVM implementation is? To test this, I test performance on TPCH query. TPCH query 1 is aggregates on a large table like this. Select to this query took about 10 seconds. And by creating materials view, the response time is 1.5 milliseconds. So it enables quick response. However, refresh of this materialized view took about 36 seconds. So it takes so long time. On the other hand, using incremental view maintenance, when one tuple of the base table is updated, it takes only 70 milliseconds. So, and the view is updated automatically. The view is updated so rapidly. This is more than 2,000 times faster than normal refresh. In another example, using TPCH query 9, this is an aggregate on 9 tables join. The refresh of the materials view took 6 seconds. But IVM took only 30 milliseconds. It is more than 200 times faster than the refresh. Okay, IVM is so effective. Okay, I'll explain the basic theory of IVM. View definition can be described with relational algebra. For example, simple natural join view using table R and S is represented like this. And when a table R is updated, its change on table R is represented like this. This inverted triangle, inverted delta is nabla. Nabla R means tuples deleted from the table. And Greek delta R. Delta R means tuples inserted into the table. Using these table changes, we can calculate changes on view, now V and delta V. And by applying these changes to the view, we can get the latest state of the view. Using this example, there's two tables, R and S. And this is a natural join of them, V. When R is updated, now R and delta R is like this. And using these changes and table S and V definition, we can get now V and delta V. This is a changes on the view. Finally, applying these changes to the view, we can get the latest state of the view. This is an IBM process. About timing of view maintenance, there are two approaches: immediate maintenance and deferred maintenance. In immediate maintenance, materialized view is updated in the same transaction where a base table is modified. In deferred maintenance, the view is updated after the transaction is committed. For example, when the view is accessed via select statement, where as a response to user command like refresh materialized view command, where view can update it periodically in background and so on. However, we started from immediate maintenance approach because it requires less number of calls. Deferred maintenance, implementing deferred maintenance needs a mechanism to manage logs for recording change of base tables. It is not trivial work, so starting immediate maintenance is easier than deferred maintenance. So we decided to start from immediate maintenance. This is an overview of our implementation. There are three steps. First, when base table is modified, the changes on table is extracted. And using these changes and view definition, we calculate changes on view. And applying the change on view to materialize the view and update the view. In our implementation, we use after trigger and transition table to extract the change on table. And calculation of changes on view is based on relational or bug algebra. And changes on view is applied to the view using SQL query. Okay. Create incremental materialized view. This is a tentative syntax to create materialized views with IBM support. This incremental keyword is our extension to the original syntax of created materialized view. And when view is created, after triggers are automatically created on all base tables. For insert, delete, or update command as statement level triggered with transition table. This transition table is a feature of after triggers. Using this feature, changes on tables can be referred to in the trigger function like normal tables. There are two tables. One contains tuples deleted from the table, and another contains tuples inserted into the table. In theory, these two tables are corresponding to number R and date R respectively. Using these changes on table, delta table, we can calculate delta on views. For calculating delta on views, we use a view definition query with some rewrite. In this rewrite, the modified table is replaced with transition table. For example, this is view definition, and this is modified table. And in return query, this table is replaced with transition table. In addition, the multiplicity of each tuple is calculated by using count as the aggregate. And the result is like this. This IVM count column is multiplicity of each tuple. And finally, these delta on views is applied to the view. When deleting tuples from the view, tuples in the view are deleted as many as the specified multiplicity. The same tuples in the view is numbered and using row number window function. There are three same tuples, but only two tuples are deleted because the multiplicity is 2. When inserting tuples into the view, tuples are duplicated to the specified multiplicity. This is performed by generate series functions. For example, this tuple's multiplicity is 2, so this tuple is duplicated 2. Here, I'll show the result of simple performance evaluation. We use the two materials view with the same definition query, but one is a normal materials view and another is created with incremental option. First, the refresh of the materials view took more than 10 seconds, so it takes a long time. But after creating an index on the materials view and updating a tuple in the base table, it took only 80 milliseconds. Of course, the materials view is updated automatically and correctly, so the view is updated rapidly. On the other hand, here we created an index on the materials view. But after dropping the index, the IVM updating a tuple in base table took 4 seconds. So although this is faster than normal refresh. Normal refresh took 10 seconds. It is 4 seconds, so it is faster than normal refresh. But for efficient IVM, we need appropriate index on materialized view. This is an important point. Next, I'll explain aggregate support. Now we are supporting built-in count sum min max average with or without group by clause. When using group by clause, expressions specified in group by clause must appear in the target list. In aggregate view, views have one or more hidden columns. For example, the number of tuples in each group is stored as hidden columns. In addition, for average aggregate, we stored the value of count and sum as hidden columns. When view is maintained, first, aggregates are performed on table deltas, changes on tables. And aggregated value in the view are updated using the result. The way of updating the aggregate value in the view depends on the kind of aggregate function. This is an example of updating aggregated values in the view. For count or sum aggregate, we can easily calculate the new value by applying the count or sum calculated from the data table. To get aggregate value, we need some value, new sum value, and a new count value. So these two aggregate value are stored materialized view as hidden columns. For min or max aggregate, when tuples are inserted, for min, list value between the current min or min calculated from the delta is used. This is similar to max cases. And when tuples are deleted from the view, if the existing min or max in the view is deleted from the view, it needs to recompute the new value from base table. So in this case, it takes a little time than other cases. Here is a simple performance evaluation on aggregate views. There are two material views of aggregates on PG bench tables. One is normal material view, and another is a view created with incremental options. First, refresh of the material view took 30 seconds. However, updating a base table took only 30 milliseconds. And the view is automatically updated, and the content is of course correct. So the view is updated more than 1,000 faster than refresh command. Great. Next, I would like to explain outer join supports. In outer join views, there are null extended tuples. It is called dangling tuples. This appears when the join condition does not meet. So when tuple is inserted in the table, dangling tuples might be deleted from the view. And when tuples are deleted from the table, dangling tuples might be inserted into the view. So it needs some extra work. So outer join view is maintained by two steps. First, calculate and apply deltas as similar to inner join case. And then additional dangling tuple handling is performed. We implement this based on an algorithm in Watson and Zhou with some theoretical extension to allow duplicated tuples because original algorithms don't allow duplicated tuple in view. Here is a performance evaluation of inner and outer join view. We create two materials view. One is inner join and another is use full outer join. Also, there are three conditions about index on the materials view. First, there are no index. Second, the view has an index on the primary key columns of base tables. And third, view has additional two index on columns used in join conditions, as well as primary key columns. This is a result. In both cases, refresh took about 8 seconds, so it takes a long time. And in all index condition, IBM is faster than refresh. But for effective maintenance, an appropriate index is required. Without index, it takes 2 or 3 seconds, but with index on primary key columns, the IBM is so effective. In addition, with additional index, the execution time on outer join maintenance is almost same as inner join views. So we can update both inner and outer join views with almost same cost. Finally, I'll explain subquery support. Now we are supporting exist clause in fair. Well, for implement this, the row number count of exist subquery is stored as a hidden columns in each tuple in the materials view. And when a table in this subquery is modified, in this case, table 2 is modified. If the count becomes 0, the tuple in the view should be deleted. Otherwise, the tuple remains because this exist condition is true. Also, we are supporting simple subqueries in from clause and simple CTEs, that is with clause. Simple means subquery or CT contain only selection, projection, or inner join. Aggregate or outer join is not supported in simple subquery. As the restriction of the current implementation, we were not supporting aggregates other than built-in count, sum, average, mean, and max, and having clause and complex subqueries and CTs, including aggregate, outer join, and window functions, set operations, order by clause, limit offset clause, and not supported. As for outer join, we support only simple equijoin, and it cannot be used together with aggregates or subqueries. And as for exist clause, we support only or exist. We support only and exist, and we don't support or exist or not exist. And exist clause cannot be used together with aggregates. We test how many queries in TPC benchmarks are supported in our implementation. As a result, 9 of 22 TPC-8 queries and 20 of 99 TPC-DS queries are supported. In both cases, order by and limit offset clause are ignored. In TPC-DC cases, 33 queries failed due to complexities, and 11 queries failed due to aggregates in subquery. So, relaxing the restriction and supporting more general view is one of our future work. Performance issues. As shown in this talk, using IVM, materialized view can be updated faster than refresh command. But appropriate index are required on materialized view for efficient IVM. So, in the latest patch, appropriate index is created automatically when the view is created, if possible. So we don't have to make an index by yourself in this case. In our implementation of IVM, views are updated for every table modification. So there are impact to performance of updating table. So it's not suitable for write-heavy workload. Instead, it will be useful when update is not so frequent, but users would like to know the analysis result immediately. As other features, we support with no data option. This is an option of create materials view or refresh command. With this option, the materials view becomes not scannable, and triggers on view is dropped, so the view is not automatically updated even when a base table is modified. So this means the performance of updating table is not affected by IVM. It is useful when large data is loaded on a base table. For supporting low-level security, when a view is updated incrementally, its base tables are accessed with the view owner's privilege. And PG dump and PG restore is supporting this new syntax, create incremental materials view, of course. Okay. We explained our implementation of incremental view maintenance IPM on PostgreSQL. This enables rapid and automatic update of materials view, and it is faster than normal refresh command. Also, of course, you don't have to write trigger functions by yourself. The patch is discussed on mailing PDSK hackers developers mailing list, and we are targeting PostgreSQL 14. We also have GitHub repository, and there are Docker images on Docker Hub. This can be used to test our IBM. So we would greatly appreciate if you would test the IBM and you could give us any feedback. Okay, that's all. Thank you.
Hello, I think that we get back for the QA session, and welcome Nagata-san. And we have one question in the chat so far. It is, I think that it was not, it was answered during the talk already, but still. It says that what is the performance impact and what is the overhead of maintaining this incremental materialized views compared to without this incremental feature?
Okay, well, even though there is no data in slide, then I forget the real the performance, but exactly there is an overhead of IBM. So every time the base table is updated, view is also updated. So the overhead is large, and at least it is slower, at least a few times slower than the normal update of view.
Yeah, I think that it is expected then when you update view together with data, then it takes some overhead. But if we choose to do this deferred materialized view update, so can we neglect this overhead, or it still persists?
Are you asking about optimization?
No, I mean that if we update this incremental view immediately with the data, then of course we have this overhead. But if we do deferred updates the data, then I think that the overhead will be lower.
Exactly. So reduce overhead of IBM, we need deferred maintenance approach. So I think this is a future work. So I would like to implement this for more practical implement for more practical.
So we have no questions, but I will use a chance to ask my own questions for you. And first of all, I want to say that it is interesting that there is such a solid theory, this relational theory under doing this incremental views updating, because so I think for it is interesting. At the first sight, it seems like maybe a simple topic, but internally there are a lot of problems. And I think that you talked about it in your talk, but I cannot get entirely. So how we calculate this delta? Because I think that if we have no internal like index or something like that, then to create this delta of changed rows, which we need to process to do an update, we have to do an entire sequential scan of the table to calculate this delta. But how it is implemented in your patch? So do you have some kind of index where you put the changed rows?
Well, basically, when calculated the change on views, we use view definition query just after replacing modified table with transition table. So if the base table has an index, this index is used, and the delta of views is calculated rapidly, but there is no index on base table. If there is no index on table, to calculate view delta will take a long time. Yes, so yes, for efficient IBM, we also need appropriate index on table.
So, okay, in other words, we put these modified rows required for incremental update in some transient table, and after that we pick them from there and do this update.
Well, sorry, could you rephrase?
I mean that in other words, we if something is updated on this data table, we put these rows into some transit table,
Yes.
at some like, and after that we pick them from this transit table and do this incremental update.
To the same. Perform to the same query. Sorry, I didn't catch your question. Sorry.
So okay, maybe we can ask. I can ask another question from the chat because it was on my list also, and it says that is it like natural restriction? So we cannot do an incremental update for any query. So we have to manually add implementation, for example, for some aggregates. So, for example, we cannot support like user aggregates, or there is a chance that we can implement like general solution to support all possible queries for materialized views in Postgres.
Wow, this question is about view definition query restriction.
Yeah.
Yes. Well, okay. We are trying to reflect these restrictions, but I think it is a bit hard to treat complex subqueries, including aggregate or distinct. So to handle these complex queries with complex subqueries, we will need to handle nested IVM. That means materialize some expression in the views and incrementally by incrementally maintaining the sub-expression in the view, we can handle more complex view definition query, I think.
Okay, thanks. So I think that the work is in progress, and there is a chance that it will be implemented maybe one day. I don't know that I think that I have no additional questions, and there are no questions in the chat. So I want to thank you again for your talk and for answers. And also I want to advertise this thread in the Hackers. And I think that it is really, I think that it's one of the hot topics, and it will be interesting to implement this feature to improve speed of some analytics and so on. And reviewers and commenters and testers are very welcome to this Hackers thread to try this new feature and to help testing and implementing anything there. So thank you again. And I want to say that we have some special chat. It is called Special Chat, and all participants and speakers can communicate there. And it is like Clubhouse, but on our platform. And you can talk with speakers using voice. And during all days of conference, I have not tried it so far, but I'm going to get there and try it. So thank you. And we have a half an hour break before next talk. And there will be a new chairman there. So I have to say goodbye to you for today. Thanks.
Thank you.